This was a great introduction and pushed a little bit more pressure on me. So I definitely don't belong to these 18 previous speakers. I'm not at the same level, but let's take it as a message. If you work with passion and devotion, anything can be achieved, even invited as a Nonveiller lecturer. So thank you again to the society, to Sonja, Leo, and other colleagues. Drage dame I gospodo, kao osoba rođena u Jugoslaviji ne mogu samo da pričam na engleskom, treba da rečem barem da vas pozdravim na našim jezicima. Drago mi je što ste me pozvali i ja se nadam da ćemo zajedno uživati u tim, šta ja znam, 60-70 minuta. Let's switch to English back because this was the decision and we have some foreign guests which I also like to welcome here. So the topic, so Sonja asked me to speak about landslides that were triggered in 23 when there were a lot of rain and floods. And I will show you some of that, but I took the opportunity to show you something more from my professional life and career. It's almost 40 years, and they passed really quickly, so I don't know where all these numbers that Sonja mentioned and all these functions that I had when all this happened. And here are many young people, I don't know what I'm talking about, the older one they do, but you will come after us. So just use your time wisely. So the role of advanced technologies, what do I mean by advanced technologies? It is something that Professor Nonveiller didn't use. It was not possible for him to use it because it didn't exist. And there are technologies that are still today, maybe not in everyday use. We can use it. You use at least some of them, yeah. It's not something that is that has been developed maybe 5, 10 years ago. It may be 25 or something like that, but it's still not in everyday use. Why? What is forensic and why forensic? In Slovenia, research projects were always difficult to obtain. So we, at the faculty, we devoted a lot of time to professional projects, to demanding professional projects, and from these projects, some research projects were developed or some knowledge was obtained, and I will share this with you today. And why forensic? Because predictions about the future are difficult, especially in geotechnical engineering. When you predict settlements, forces, especially settlements, movements correctly, we are always happy because there are so many uncertainties in our models. And yeah, it is always a little bit easier, at least, to explain what happened in the past. So the changes from last decades are mostly, but not exclusively, bound to information technologies. We've got internet that Professor Nonveiller we didn't have at the beginning of the career. And then were databases, geographic information system, building information modeling, artificial intelligence. Then we have satellites flying above us, taking pictures and collected massive amount of all sorts of data. Then we have numerical model. Yes, these existed started from maybe 1960s, 70s, in the 20th century, and continuously improving still today, and we use them a lot. Then we have laboratory equipment, which is always, constantly improving, taking advantage of new developments in electronics and so on. And then we have monitoring tools that equally develop. And we do testing of structures. For instance, I will talk about testing of anchors. And then we have developing construction machineries and so on and so on. And all these tools, we believe, will take some burden or workload from our shoulders, but what happens actually is just the opposite. You can do more, so do more. This is usually the message. You have all these tools and machines, you can produce faster and better. Yeah, so the workload is never reduced. I think it's rather different. So when I started to work in geotechnical engineering in mid-80s, it was not unusual to get, still in some reports, manually made stability analysis. Then this is a picture from the software that Bojan Majes and I developed in the 80s. And then now today we have all these fancy, colorful software that does it much better and with much more options. And today we can also do 3D fancy calculations. Here is a solid structure interaction of a bridge with a creeping slope, so really advanced stuff. So what do I mean by forensic geotechnics? So it's basically about explaining why something happened and why a behavior of a certain structure, geotechnical structure, was different than expected, or why failure occurred. Why was the effect on nearby structures or pipelines higher than expected, or what caused a certain discrepancy or change in behavior or property. Forensic may also include legal aspects between court issues, so settlements of disputes. This is something that I was involved, not many times, but sometimes, and this is the least pleasant side of the story, and I will not talk about that. So the purpose of forensic engineering is basically to find the reason for non-compliant behavior, but also to get experience from this documented experience, past experiences for future projects. Usually, when something went wrong, we have to design the remedial measures, and when things go to court, attribute the responsibility. We are here to keep the memory of great Professor Nonveiller, and I chose the topic on forensic geotechnics because there is a fil rouge of Professor Nonveiller's life, professional life, and it's the explanation of what happened in Vaillant landslide, why this was triggered, and so he tried to explain the behavior. I believe that most of you are aware, but I will shortly repeat this story and present the role of Professor Nonveiller as I see it, and I might be wrong because I didn't know him very well. Although I met him once in Ljubljana, he was there at the committee for a defense of a PhD thesis, so I was able to meet him at least once at the beginning of my career. So Professor Nonveiller wrote about this event, so this major disaster, geotechnical disaster, from 63, and this disaster happened on October 63, 9th of October in 63, and the same year he already wrote a paper, I believe this was in Građevinar. And until 92, so for 30 years, this event kept him busy. I don't know why he started to study this event. My belief is that it was just a professional challenge. Maybe he was asked by someone to come there and help with the forensic analysis, or it might be just his, that it was his interest. Because a few years before, he did his PhD on stability of non-homogeneous embankments. So, stability problem, a huge stability problem, might attract his professional interest. And also he spoke fluently Italian and German. And since Austrian engineers were present and some reports were in German, and it's located in Italy, so there were also Italian experts, he was a perfect man, besides, of course, his professional knowledge. So he wrote 11, 12 papers on that we can find, are listed in the beautiful book that our colleagues published. And here you see the Vaillant Dam. It is a concrete arch dam of 262-meter height. And this is before the landslide, and this is after this disaster. So you can see that a massive amount of rock and soil slid into the reservoir. And yeah, you can see it here with the data. So the reservoir was supposed to have 160 million cubic meter of water, and the rock mass that slid into this reservoir when it was, well, not completely full, but close to that, displaced about 50 million cubic meter of water, and with the splash of water being supposedly 250 meter high, literally flushed away the village here. Here's the dam, here's the landslide, and here's the village of Longarone. And yeah, so killed about 2,000 people. Dam itself remained unaffected. And this is still considered one of the major geotechnical disasters worldwide. It's still attracting interest of researchers. So there are still papers published on that, improving the, well, we have heard about the importance of engineering geology. So about engineering geologists who try to explain the previous situation, how the evolution of this space was, speaking geologically, what was here before and what was the cause of the landslide. Professor Nonveiller went there, collected all the data, and analyzed them by himself. I think this is so important that we, as a geotechnical engineer, we want to explain what happened. We really collect all of the data available. Don't leave out any number. It may not fit at first to the picture, but we have to understand which data are correct, which are maybe misleading, and when we do this process, and it's so important that we do it really by hand alone, I mean by hand, use Excel spreadsheet to make that curves like this one presented in Nonveiller's paper in '87. So here, what did he do? He plotted movements of certain points here on the slope that later became a landslide, and he plotted it together with the height of the water in the reservoir. So it is clearly seen that any lift of the level, of water level, was connected with increased rate of movements. And when it was lowered, movement stabilized. Next, filling up to the same level didn't produce much of displacement, but then when they exceeded the previous maximum level again, and so until 9th of October. He also noted here, these dots here mean earthquakes that were triggered. Why are these earthquakes, why are earthquakes happen during the filling of the reservoir? Because probably on the future slip surface, there were some compact blocks that had to be sheared off until finally all the slip surface was free, smooth, and the mass slid into the valley. There was also a nice paper from your conference in 2013 by Professor Tanya Roe-Bonacci about the role of Professor Nonveiller in explaining this event. So Professor Nonveiller was actually the first. Imagine, there was a project, dam was constructed, they started filling the reservoir, but nobody did some tests in the laboratory. Of course, the advantage of forensic engineering is, later, that he was able to see the material along the slip surface, took the samples, tested them in the laboratory to get the material properties. He was first to make systematic stability analysis. And later, because one question intrigued him a lot, why this movement was so fast. He started to think that maybe due to friction of a massive amount of material traveling downwards, so this friction generated heat. Heat turned the water into the vapor, and so there was a pore pressure buildup, vapor pressure buildup, and also he considered softening of the material along the slip surface due to this extreme heat. And not only that he thought about all this, but he developed an analytical method to calculate the rate, the speed of the traveling landslide, and got with the final number. So it is amazing. I mean, we have already heard many things about Professor Nonveiller, but it really shows a man that was into the topic. So he was fully engaged. So he did thorough and systematic collection of and analysis of data. He did additional in situ observation and laboratory testing on his own, with his group, of course. And we can see that he had profound theoretical knowledge already on soil mechanics, but he was not happy with that. He was not able to explain everything till the end. So he searched the literature, he incorporated other theories, other physical phenomena into description, mathematical description of the process, came out with the solution. So it was really out-of-the-box thinking, and sometimes it is necessary. So not to stick with what we are trained to do on everyday base, but he went beyond that in order to explain what happened. So I told you that there are still many papers speaking about Vaillant case, and there is one statement from the paper of Dykes and Bromhead from 2020, and it is a paper with the title Lessons from the Vaillant Landslide. And they say, the lessons of Vaillant for engineering practice have largely been learned. The ultimate lesson being that one should proceed cautiously with any engineering works for which failure is likely to be disastrous. Again, it's a prediction about the future. Huh? Do we know how it is going to happen? But if there is a remote chance that something goes very wrong with disastrous consequences, we should really proceed with caution. Okay, now to the topic that we discussed in advance. So floods in Slovenia on 3rd and 4th of August, well, till 6th of August 23. There was a heavy rain, so up to 300 millimeters in the whole 3 days, but most of these precipitations occurred within 6 hours. So 2/3 of the country was affected. Remember, it was August, yeah? I was in Lukaran, in Ugljan, on my holidays. It's not usual, so we usually have this in autumn. Over 13,000 houses were damaged. 8,000 people were evacuated. 350 families have had to move permanently. There is 4,000 kilometers of watercourses damaged. Nearly 2,000 kilometers of road needed refurbishment, and thousands of landslides were triggered. There are estimates that there are about 10,000, but it doesn't really matter. There are probably around 350 to 400 that will need some kind of attention and engineering approach. The official numbers say that about 3 billion euros of damage occurred during this event, and 1.3 on watercourses, 1.16 on built environment, so houses, factories, infrastructure altogether. So one good thing of, good reaction of, let's say, government or governmental agencies was that aerial images of all the areas affected, so along the watercourses, we can see another, well, color of the photo. So this area around the watercourses was documented using aerial images immediately, so a few days, on 7 and 8 of August. So we have frozen image in time, and we can always go back and see what happened within these areas that were documented. Around Kamnik, this is an image about 2.8 square kilometers is presented on these figures. And you can see many landslides, so many brown areas. There was a colleague, Jernej Jež from Geological Survey of Slovenia, coloring all these. So he went from one to another, and on these 2.8 square kilometers, he counted 50 landslides. Many of those don't affect anything. I mean, they're just there in the woods and on the free space, on green fields, and yeah, some of them affect also buildings and roads and so on. Here I will show you two. I will move it like this. So the road, you can see, stays at the same place. So the old picture and the new one observe these houses, so they moved for about 20 meters during this event. And there are quite some places like this. At the end, the result for this house is here. And of course, the people will have had to move. I didn't mention the reaction of civil protection was so good that despite the severity of the event, only, sorry to say so, only 4 people lost their lives. I will only mention one landslide a little bit more into detail. So this, again, a picture before the event and after the event. Here you see the village, and you can see that the river Savinja, its course was here. And then you can see that the water split here at this point, and partly runs in the previous course, and partly was diverted through the road and through the village back to its original course. What happened? Observe this point here, so this curve or bend of the river, and observe it now on the second picture. You can see that this original river course at this bend was here, and now at this course it's smoothed. So part of this slope has been pushed by water into the water stream. This blocked the waterway and pushed the water diverted the water on this road, and the water devastated the village. A little bit more in detail. So again, this is the location. This is the picture after the event, and you can see how the water split here on two different courses. Maybe if you followed the news at that time, most of the picture with these tilted houses came from this village. Well, the story is that this village was not here before 1950. There was nothing. All these remote sensing techniques allow to construct the digital elevation models, and comparing two digital elevation models, we can see the difference where the material was deposited, the blue region, and where it was taken away, so this yellow, orange. So here the height difference was up to 30 meters. This was really done a few days after the disaster, so it might not be very precise, but nevertheless, it shows what happened here. LiDAR images are so interesting and good to use. We have in Slovenia the entire country covered with these LiDAR images from 2015. So now it's about 10 years. And yeah, now they do the second series of pictures, and will be available, I suppose, within 1 year. And this is so good. You know that archaeologists are looking for ancient remains using this technology, so details can be seen. And here we can see that this area from which this particular landslide was triggered, this is an old slide. This is an erosion process going on for hundreds of years or millennia even. And this was only just one of the sequence of the events in geological history. And well, it's a disaster in the views of humans. We can also see previous landslides using this technology. This is amazing, I mean, because you cannot miss it. These LiDAR images are great for our profession, and I advise, or better to say, whenever I have to go somewhere on a site, before I consult all these publicly available data to see if anything can be understood from these publicly available data of aerial or laser image scanning images. If I show you back this location, so this is here, huh? You don't see anything, it's forest, so you don't see it just like that. You have to have this LiDAR image of, which is where the trees are filtered out, and then you can see the morphology of the ground. This particular landslide was already investigated. Some 7 boreholes were drilled, and piezometers and inclinometers installed, and now this is going on from, well, 1 year. And we can see that, for instance, the image of the inclinometer here on the right side is located here, and shows relatively clearly now, although there is maximum 80 millimeters of movement, that probably there are 2 levels of sliding. And these 2 levels are here marked with the red line. So the lower one coincides well with the expected slip surface, but we have another level of sliding here, about 20 meters high. So one is at about 35, one about 55 meters deep. It's a huge landslide, and most probably what will happen is the village will be moved, and this slope will be protected against erosion and the rest will be left to Mother Nature. Previous flood in 1990, close to, it was not as severe as this one, but nevertheless one of the major floods. At that time, the governmental agency decided that people have to go on site, experts, and take readings, take the elevations of the water on all the houses along the affected rivers. And this event is still, the documents from this event is still used to calibrate hydraulic models for the river courses. It was not done this time, except my colleague here, Rok Fazarins, he is real passionate about his profession, and he went to some locations and document out of his interest and because he was responsible for some areas, and then he asked colleagues to take readings. Although today it's much easier. We have these GPS devices, so taking readings and documenting them into databases, it's much faster today, but then it was done, now it was not, which is a pity. And one more thing, damage inventory was done in a very old-fashioned way, so on using a piece of paper and filling out only some basic data. I have seen the list of documents. I have seen the list, and it says like, by Janko's 15,000 euros. That was an Excel line, thank you. Excel line in this database. So today, where we all have the gadgets in our pockets that can document the location and can take pictures, we didn't take advantage of that. And today you have the app on the, we have the apps for everything, and you can see here, so we have codes and technical options to document landslides or any disastrous events. So speaking about the positive and let's say negative, I placed the room for improvement. There is always room for improvement. So positive aspects were that, first of all, fast and effective response of civil protection. This was so important to people that were not left alone, and it was really, this was really effective. Then on-time application of remote sensing, so we have documented the situation. This is good. The infrastructure, mainly the roads, were repaired very, very soon. So the roads were trafficable again within days and weeks. And we learned that water needs space. We cannot build our houses, factories, anything else, our built environment, and use all the space that was by nature devoted to water. Water needs space. It will take it anyhow. My colleague Rok Fazarins, he's brilliant mind, and people used to say, well, the old people know where we should or should not build. And he says, well, it's not completely true. The truth is that what was not built in the correct location doesn't exist anymore. Yeah, where is the room for improvement? So all these, some fast remedial measures done by civil protection did not survive the next floods, which were much less severe, occurring just 2-3 months later in October and November 23. So many of those failed. Okay, when something is done fast, may not withstand the forces of time. Then the water management, so the Agency for Water Management needs to be more effective. There was no in-situ readings of maximum water levels. This is something that the people who are doing hydraulic modeling will miss in the future. We don't have database of landslides and ground properties. And the landslide hazard map, this is one here on the bottom left, do not cover the whole Slovenia. So we have landslide hazard maps for, I would say, about half of the country, but not for all of them. And these landslide hazard maps are used for the spatial planning purposes and when you ask for building permits. Thank you. I cannot come from Ljubljana not mentioning the marshland. So let's go on the next slide. Does it work? Yep. So you know where Ljubljana is on the right side, and we have this yellowish area in the center, which represent the marshland. It was a few thousand years ago. Zdenka helped me. 5,000 years ago, 10,000 years ago, it was a lake. It was a lake, and yeah, so the upper 20 meters, 10 to 20 meters are filled with very, very, very soft lacustrine sediments. Geologically, this area is a tectonic sink, so the bedrock is located maybe 100, let's say 50 meters deep and filled predominantly with alluvial deposits, gravel, but the upper 20 meters are extremely, extremely soft. On top of that, we have this nice new earthquake hazard map. So design earthquake acceleration. I don't know if you can read it. Ljubljana is in the center. The new acceleration on the bedrock is 0.275, which is a little bit higher than it was before. The map below is not an official one. But here on this southwest area, where this marshland is, the colleagues from Seismological Institute tried to, to anticipate the acceleration on the surface based on analysis of microtremors. So these are extremely small strain vibrations, and so the method is based on elastic behavior of the ground, which for such a soft soil, of course, is not true. But in this way, they came with the prediction of a maximum earthquake acceleration on the surface between 0.2 and 0.6, 0.5 and 0.6, which is extremely high, and which definitely cannot be true. Thank you. To see how soft this material is, this is a reproduction of a slide made by Boštjan Pulko, but the measurements were done by Anna Gabrc, who is here with us, on the Ljubljana Ring motorway. They did, imagine, do you have it in Croatia still? Because in Slovenia, they don't give us the option to do some test, embankments, test cuts, whatever test. You can test pile, test anchors, but testing the geotechnical structure as a whole, forget it. They say, you have all these fancy computer programs, you can do everything. So about 5 meter high embankment settled for close to 3 meters. The initial pore pressure, void ratio of this material is around 3, so the moisture content would be over 100%. So this is how soft this material is. Let's go on. And then from this very soft material, there are a number of anecdotes, actually. This was not an anecdote, but this is a real court case. We have these 4 buildings here, and 3 of them perform without any problems. And this one started to tilt, causing the inhabitants problems. Windows don't close, and so on. Then we were asked to try to understand what happened, why this is wrong, and attribute the responsibility. And at first, we didn't understand. It was quite nicely done for the private buildings. Each of those had the borehole. Well, the borehole, without laboratory test, we know it's not quite a lot of data, but at least they tried to do something. And so the only thing that we were able to do within the budget was to consult the Google Earth. And we have seen that some years before, you see this mark? This mark is here. There was a previous building, and then here was a parking place, and we talked to the people, and they said, well, here was a guy having these heavy trucks that were parked here together all the time. So what does it mean? The previous use, the previous loads on this very soft soil caused some consolidation, some previous settlements of this area under part of this building, and the rest was not consolidated yet. And so it's on such a soft soil, this is so important to understand the previous use of the location, and this was the, I mean, as a consequence, this load history of the area here under this building caused later unwanted behavior. Today we have this beautiful tool. I don't know if you know it or not, European Ground Motion Service. It's actually a radar interferometric analysis of satellite images in the radar spectrum. Europe has two satellites. One is Sentinel-1 and Sentinel-2. And this is a public service. You can just write European Ground Motion Service, and then you will get this data. Why I'm showing these locations? Because right now here is a construction site with some tens of new houses. And the owner, the client, didn't want to put these houses on pile foundations, on deep foundation reaching the higher bearing stratum. And later on he wanted a confirmation, or he wanted the contractor to promise that after he hands over the buildings to the future owners, there will not be more than 2 centimeters of settlement. And the contractor went to me and said, well, how should I react? And I just showed him the first point adjacent to this construction site and said, all right, look, this is the natural behavior of the marshland here. It's 1 centimeter per year. You do nothing, you have 1 centimeter per year. And now you imagine, what are you going to sign? I don't know what the discussion was later. The construction is going on, and well. Speaking about some new technologies, I know that flat dilatometer test is also used in Croatia, and with the addition of the seismic unit, so you can measure also the G0, the shear modulus at the very, very small strains. You get quite a good first profile of stiffness and strength, and then of G0. So this is one of probably the best tools that we have, at least for soft soil, clays, silts, and sands. We can have a whole profile. The measurement is taken each 20 centimeters, which gives you a good profile, together with the few laboratory samples, so you can compare and see. You can do a very good prediction, even about the future sometimes. Well, and I cannot resist to mention the resonant column test device that we have, and the work of our PhD student, who is also ill and is not here, Timotej Jurček. Our idea was, I showed you initially, we have very soft soil, something special, not too extremely special. There are even more soft soils in the world, but for our region, I think is one of the interesting places. And we have high seismicity, so we really wanted to know how this material behaves in this small strain range. And the question was how this stiffness decay curve looks like? Because based on these two curves, we can anticipate the amplification of earthquake acceleration traveling from bedrock to the surface. This curve can be described by this analytical expression, and the only parameter is actually gamma 0.7. What is this gamma 0.7? It is shear strain at which G0 is reduced down to 70%. So I will just give you the result. We have a set of proposals from different researchers how this gamma 0.7 is what should be, yeah, based on investigations of different soils. And we have mostly used this EPRI curve, this one. And we always feared and felt that this particular soil can be different, and it was. Now we have the confirmation that it's different. So gamma 0.7 is lower than any published results. And, well, this is one information and one research result, and the other one we have numbers. So now we can more confidently do the analysis of this earthquake amplification. Another thing is, observe, this is plasticity index. And these are results on samples taken from just 4 different boreholes in Ljubljana marshland. So 4 boreholes, the entire number of samples is around 60, and you see the diversity, plasticity index ranging from 10 to over 90. So this is our marshland. Sonia mentioned that I did some work on ground anchors. And again, just a short introduction so we can follow the further slides. Ground anchors are tested. Actually, each ground anchor is tested, and by different tests. So you have acceptance tests, suitability tests. So the investigation of an anchor is done in several stages of loads, and at each stage of load, the force is maintained constant, and then at the anchor head, the displacement is recorded. And if we do it in logarithmic, we plot it against the logarithm of time, then we can calculate this so-called creep coefficient alpha, so difference in movement divided by difference in logarithm of time. The bearing capacity of anchor is determined as the force leading to a creep coefficient equal to 2. So creep coefficient equal to 2 means we are at the limit of the bearing capacity. We have achieved the bearing capacity. And now again, forensics, yeah? There was a construction site, and it was a particular one. It was in the Flysch region where this kind of construction was designed. So we have these prefabricated reinforced concrete elements. Each of those had the place for one anchor, and since the earth pressure was relatively low due to good properties, the designer decided to use 2-strand anchors, so just 2 tendons, 2 steel strands for each element. When we do testing of anchor behavior before the systematic installation of them, we usually try to see how much of bearing capacity can we achieve, and we usually add 1 further tendon. So these were 3 tendon anchors tested, and these are 2 triangles. Yeah? Effective free length against the creep coefficient. So the creep coefficient was around 0.6. When they started to install the regular anchors having 2 strands, they got all this range of creep coefficient, even going up to 1.2, which was by the design not acceptable, and they asked what to do. Well, these anchors were installed, they worked perfectly, no problem. But the question remained. So it was triggering. Why those numbers? So we went back, collected a lot of anchor test results, did a statistical analysis, and then we were happy enough to be able to at least remotely participate through this bilateral research project, a minor one, with Technical University of Graz, who did some tests. So let's see first this statistical analysis of anchors. So what we did is a regression analysis. So creep coefficient was written as a function of force, of free length, of bond length, and of number of strands, a number of steel tendons. And all these factors that resulted from this regression analysis were statistically significant, highly significant. So no doubt about that, that this is valid. For anchors, if we take now as a reference anchor, the one having 4 strands, 15 meters free length, 7 meters bond length, and 800 anchor force, this equation would give the result. So one additional strand, so instead of 4 having 5, will reduce creep coefficient by 49%, which is interesting, isn't it? 1 meter shorter bond length reduces this factor by 12%, and even free length, which shouldn't have any effect, well, reduces by negligible 1%, but has some effect. If we plot the same results a little bit different, now creep coefficient as a function of force, but force normalized to the capacity of steel, nothing to do with soil, yeah? So force divided by capacity of tendons, we get, again, this result that creep coefficient increases with normalized force. No matter, we have 2, 6 strands, whatever. If we have a look what this utilization factor is, so I said force divided by cable strength. Cable strength is area multiplied by strength. Force is function of strain, actually. And finally, we see that we have 2 material properties of steel, and the rest is strain. So measuring the strain could tell us something. And the colleagues in Graz had the chance to install fiber optic cable along the tendons and within the grout body outside of anchors. And these are the results. So fiber optic cable can serve as a strain sensor. Each centimeter of the cable can serve as one piece of sensor. So we get the data along each centimeter of the anchor, which is perfect. We did previously some measurements with the strain gauges, but this strain gauge is installed once a meter and will never give you the same result. So along the tendon, we see what is expected. So more or less constant force, a little bit decrease here at the end. So, but let's say a constant force within the free length, and then rapid reduction within the bond length down to 0. Well, this is expected. Nothing spectacular here. More interesting is this one. So we see here in this area where the load is obviously transferred to the ground, we have what we have. We see these ups and downs. This is actually cracking of the grout. And we see, which is also clear from simple static, that we must have some compressive stresses and strains in the, along the free length. If we look how these pictures increase from low forces to high forces, we see that, for instance, this red line does not have any of these waves or peaks. And then as we increase the force, this cracked area increases. So I believe that this creep, high creep, is actually a consequence of cracking of the ground. Has more or less nothing to do with the bearing capacity of the contact between anchor and the ground. So I would say if we used, instead of grout, a material that does not crack, what would happen? That's a question that can lead to further research and further improvement of, first understanding and then utilization of anchors. The more or less last case history, it's a deep excavation in Ljubljana next to a historic building from the monarchy. It was a military structure. So this is this military structure from 19th century, and this is the new, now already constructed building. But at the time that we were involved here in the project, there was a construction pit under execution, and here is this military object. Now it is a school. So this historic object is over 130 meters long, not so wide, and has 3 stories in the attic, so it's less than around 20 meters high. Construction pit 13 meters deep, and the retaining structure was designed from 127 jet grouting columns, which were 25 meters deep, 2 meters in diameter, at a spacing of 1.8 meters. Subsequently, then during the excavation, they were anchored by pre-stressed ground anchors in 3 levels. We were invited to this construction site when, on 16th of March in 21, the people from the school informed the contractor that the building started to crack. They had 0 reading before the start of construction of some benchmark points. Let's only consult those 4. There were more, but these 4 might be important, or 3. So then immediately went to measure again, and they have seen that these points that settled most showed the settlement of 31 millimeters. So this was 1 month after construction. 85 jet grouting columns were installed, and those last 5 installed on 16th of March should supposedly cause this cracking. At first, it seems reasonable. I mean, we have construction, installation of jet grouting columns immediately adjacent to the building, so one can believe that this, yes, can cause damage to the building. But soon after that, when they inspected all the building, they have seen that these cracks extended up to 90 meters away from this point. So then this cannot be only due to these 5 jet grouting columns. But we didn't have anything to take into hand. I mean, we only had the 0 reading and the situation after 85 jet grouting columns were installed. So construction then moved from here to this corner. So additional 22 jet grouting columns were installed in week after that event. And then the authorities, on the request of the school owners, stopped the construction site. They closed it. What is the ground composition? So we had these 4 boreholes from the design stage, then 2 additional boreholes were made, and this is a picture of the material that was at the end believed to cause the problems. This is a very soft, silty gravel, so soft, loose, silty gravel. And on top, we have 10, 11 meters of very, very dense, clean gravel. So very dense layer, then some intermediate layer, and then very soft, very loose gravel, silty, and then the bedrock. Bedrock is around 25 meters, so all the jet grouting columns went down to this bedrock. So what do? You go and consult the literature, and we have seen that first that most of the literature would say that when you do jet grouting, you should be afraid of settlements, of heave, actually, sorry. And here we had settlements. And then we have found just 3 papers speaking about the settlements connected with jet grouting. First one, additional mass, additional load. Well, this one was not the case here. And then there were 2, one showing in some fine sand, 5 centimeters of settlement on a relatively short or thin layer. And then the one that was talking about particularly these loose, silty, clayey gravels, which were known to the author to potentially cause the problems with drilling and grouting procedures. So this was one thing that we did. We did 3D analysis that showed some difference from 15 to 16 March due to these 5 jet grouting columns, but did not satisfactorily answer all the questions, and particularly due to the massive, large construction site and a need of bigger model. It was impossible to model everything. And then we have a colleague at the university, a professor who is physicist, that is able to analyze the satellite radar images by using interferometry principles. And we asked him, hey, can you have a look if there are some points observed by satellites that can be used for the interpretation of this event? And yes, indeed, he was able to locate 2 points, so-called permanent scatterers, that were monitored throughout this period. And we see that there are, negligible or minor settlements before the construction started. And then these lines with colors are connected with these colors here, so we can see which jet grouting columns were constructed on each week. But what can we see is that the settlements started from the first day of construction, and they persisted throughout the time. Yeah, so there's no sudden movement of 15 or 16 of March. It was constantly going on. 15 millimeters here, and this is a point, this point, located next to this point, located next to this point, which geodetically determined 16 millimeters. So this coincided very well. So we were happy to understand that not these 5 jet grouting columns caused the cracking of the building, but the entire construction sequence, the procedure from day to day was participating. And then we did the test. We said, well, let's make 1 jet grouting column here and see the influence to the building. And we were particularly interested, so we monitored with this leveling stuff, we monitored settlements during the execution of one single jet grouting column. And we repeated it here with another jet grouting column. This was one extra within the construction pit, and then this was one which needs to be done anyway. And it turned out that this one didn't have any effect, maybe 1/10 of a millimeter, but this one here, which is about 40 meters away from the building, contributed 0.5 millimeter of settlement to this point of the building. So this was, again, a confirmation that in this particular ground conditions, the jet grouting performed several tens of meters away can cause settlements. And now the question, why? Which mechanism can transfer this displacement so far away? From this paper that suggested that drilling and grouting in loose, silty gravels can cause reduction of volume, we did a very simple 2D numerical analysis along this cross-section in somewhere in the middle, using the, very stiff material at the bottom, looser material top, and then bedrock. And we imposed volumetric change first in along the whole height of the jet grouting, and then only in upper layer and only in the lower layer. And if we do this only in the lower layer, we can see that we get practically, well, not constant, but far-reaching settlements of the model, and altogether explained what happened here. This was the final product, very nice result. So this jet grouting, massive 1-2 meter diameter, worked very well, and there were no problems anymore. So these remaining, I don't know, 19 jet grouting columns didn't have practically any influence on the building. Why? Because we had all these, most of the jet grouting columns already in place, reinforcing the soil and protecting the building. But slowly we come to the conclusion. There are still some 7-8 slides, so don't be too lucky too soon. European Ground Motion Service. When you open the map of our space, we see Ljubljana settlements, so yellow and reddish color, Ljubljana marshland. You see the consequences of Zagreb earthquake, and you see the consequences of Petrin earthquake. Well, I couldn't resist not to click on one of those points, and I've seen what I expected. So Petrin, yeah? So the blue colors is heave, and the red color here is settlement due to earthquake. So both are about 10 centimeters, and I was just randomly clicked. So this is what you expect. You have certain state, then earthquake, and then, well, the soil crust is moved and gets some new location. But then this point got my attention. I clicked some more points. It's always like that. Do you know that? Have you consulted this one? No. It's 27th of December, actually, and the earthquakes occurred on 28 and 29. I'm not saying that we can use these for predicting earthquakes, but it can be one piece of information that can contribute. And of course, every and each earthquake will behave a little bit different. I did it for Zagreb earthquake. You also have such a point here somewhere in between, but is the day after the earthquake. Well, you only have the reading each 6 days, so this is the reality. This is how it works. Geotechnical engineering and many other disciplines, technical, are all about the data. We collect meteorological data systematically for centuries, hydrological, geological, seismological, and most of these are publicly available. But what about the data on ground properties? We spend a lot of money on boreholes and other soil investigations, and this is, well, not publicly available, probably non-existing, maybe in some private archives, but I know there are many problems with that, but we have to start with that. The younger generation is waiting for that artificial intelligence can be used and assist them in making decisions, but not with reliable data. We have to start to work on that. Because, yeah, if someone decides to look to these massive databases of radar images like that and trying to understand if there is any connection with earthquakes, you cannot do it by hand. You need some powerful computer tools that work more or less in real time if you want to finally at least think that some earthquake can happen, not to predict. I don't believe in that in the years to come. So I didn't say so far anything about artificial intelligence, and I won't. I just asked artificial intelligence, one of those large language models, please list all the papers written by Professor Nonveiller on the topic of Vaillant landslide and summarize his role in explaining what happened. And here is the result. He gave 4 papers that with directly these words don't appear on his bibliography, so they're not existent. Maybe it's translation for Croatian and so on, but in this form they don't appear, those 4 papers. Otherwise, if you read the text, it's wonderful. Professor Nonveiller authored several papers and reports on the Vaillant landslide, focusing on the geotechnical and forensic analysis of the event. While I cannot provide an exhaustive list of his papers, some of his notable works on these topics include. It's so nice to read, isn't it? And then you have the second part of the answer. Professor Nonveiller played a critical role in the forensic analysis on the Vaillant landslide. His contributions include geotechnical and so on. If you just read one, for instance, lessons for engineering practice, again, it's so nice to read. Nonveiller's analysis provided valuable lessons for the engineering community, particularly in the design and monitoring of large dams and reservoirs. He stressed the need for thorough geological investigations and the importance of monitoring slope movements in real time. Perfect. So for a secondary school student, excellent. I mean, you cannot do better than that in writing. And why I'm thinking why it works so well, because there are gazillions of texts on the internet available for artificial intelligence to learn from. If we want to use artificial intelligence in geotechnical engineering, we'll have to work on data. And hopefully in 50 years, it will work perfectly, but not before we provide data. Yeah, we have beautiful tools now, computing tools, tools to manipulate and to analyze and to present massive amount of data. So embrace everything. So use everything you can. But do not forget the fundamentals of state of good old practice. So you have to put a problem in your brain. It is still the ultimate machine that we have. There is no better one, and it will stay like that for a long time. We must be actively involved in solving any challenge, engineering challenge. I mean actively, mean precisely that. With all your capabilities, try to understand, try to analyze, try to explain, and work on that. Insist to thoroughly analyze all data and understand them within the concept. Because at the end, when everything fits together, the data will tell the story. So when everything fits together, then you have it. Professor Berland, one of the examples of professors in geotechnical engineering, he wrote at least 2 excellent papers on educations of geotechnical engineers. And he proposes to use and he used during his lectures this so-called geotechnical triangle. So he believed that pillars of any geotechnical design are the following: ground profile, observed behavior, and appropriate model. So during this lecture, I have shown you something about how to get information about this ground profile. It's a flat dilatometer test with the seismic device. We have seen the remote sensing tools that can give us data about the ground surface, but there are many traditional tools. Then observed behavior, we have seen again, SDMT, resonant column device. We have mentioned LiDAR. We have mentioned GPS on the fiber optic cable. And then appropriate models. We have plenty of models, but I don't only mean numerical models. I have shown you an analytical model on this shear strength, shear modulus reduction curve. And well, it can be artificial intelligence. Everything that can assist us, but it's only assist us. We are finally the ones who will have to solve the problem. And we do it with our brain. Everything here is just a tool, and artificial intelligence is just yet another tool. Just let me thank first to, well, my professors who brought me here, and well, I'm really thankful to have that I can work with a marvelous team of people. So here, Bostian, who is ill, could not be present. Sebastian is here. Timotei, whose results I have shown. Jasna, Matej, Barbara, and myself. And yeah, it's, as Professor Nonveiller said, without a team, you're nobody. Only a group is an organism that can achieve certain, even though small results. And nothing is for granted. I mean, having people around that can assist you and force you, stimulate you to work, and continue to work, this is the most that we have. Thank you so much.